Welcome, everybody, to Chapter 3, Physical Geography and Landforms. Let's get started, shall we? I'm going to give you a brief overview and introduction. We'll take a look at Earth materials, rocks and minerals, consider the length of geologic time, look at continental drift and plate tectonics, and also look at the mountain building processes, as well as the gradational processes that wear those landforms down. And then we'll take a look at different types of landforms in landform regions. Well, some objectives here. Characterize the three classes of rock. I bet you know that already. What's folding? What's a joint? What's faulting? Uh, Illustrate how plate tectonics relates to earthquakes. Why is it important? What's a tsunami? Compare the effects of mechanical weathering versus chemical weathering on distinct landforms. Look at groundwater erosion, how that's different than surface water erosion. There's a term for that. Also, let's take a look at glaciers and how ice is an erosional agent and creates particular landscape. And then also we'll take a look at the landform features uh, such as deltas, alluvial fans, natural levees, all these things deposited by running water, and then back to moraines. That goes along with glaciation. And we'll take a quick look here at the Monument Valley in the Four Corners area of the United States. This is part of the Navajo Indian Reservation. Oh, what's that on the right? That looks like a butte. Isn't that a butte? Well, the study of landforms is called geomorphology. It looks at how human beings can influence landscape development and also some problems associated with human adaptation to landforms. A big part of geomorphology considers natural hazards and how we deal with the natural hazards, how we plan around things like earthquakes and river flooding and rivers changing direction and so forth. This very important subfield of geography and geology termed geomorphology. Geo meaning earth and morphology meaning shape. So how did the landforms get their shape? I always think that geomorphology is the most fun part of geology. See, you don't have to have an extensive background in understanding the chemistry of rocks and minerals to see the big picture part of geomorphology. You don't have to be a professional geologist to understand the natural world and how it got that way. So we're looking at the big things. You have continents that are drifting around, crashing into each other, heaving up mountain ranges, and then they'll be worn down by the erosional processes, making distinct landscapes. So looking at those big things, you don't have to have a precise knowledge of the chemical nature of the different minerals. Now that's an important part of geology, but we don't have to concern ourselves with that here as much. Well, it's difficult for us to visualize the deep time that's associated with landscape changes in geology. What's the age of the Earth? In case you see that question, it's about 4.6 billion years old. Now, in understanding landforms, it takes millions of years for mountains to be created and millions of years for the mountains to be worn down, although there can be abrupt changes within human lifetimes. So sometimes a volcano can come up seemingly overnight. And after major earthquakes, there can be a major shifting of the ground. And sometimes there's a shifting in the ocean of the sandbars and the landscapes that we try to build on there. All right, but for the most part, though, we have to look at long periods of time to look at the forces that shape these landforms. Well, after telling you that you don't have to have an extensive knowledge of rocks and minerals, you will have to have some knowledge of rocks and minerals. So we'll take a look at a few of the basics involved. And I'm wagering that most of you have already seen much of this already. Well, first off, what's the difference between a rock and a mineral? Well, a mineral is naturally occurring, it's inorganic with a particular chemical composition and internal crystal structure. A rock is a aggregate of one or more minerals. Now the metals, such as copper or gold, come from mineral ores, but these ores, once purified, the metals are no longer crystalline, and so we don't consider them minerals at that point. All right, let's take a look at a few rocks. Well, let's see. There's the igneous type basalt. There's no pepper though, just the basalt. Uh, Shale is a sedimentary rock. Limestone is sedimentary, and gneiss, or it's my niece, is a metamorphic type. All right, let's take a look. Uh, Igneous rocks. Well, there's a distinction between intrusive igneous and extrusive igneous rocks. These are the rocks that form from molten uh, earth material. Uh, as magma hardens inside the earth, it forms intrusive igneous rocks. For example, granite, as opposed to the extrusive igneous. It's extrusive, meaning that it solidifies outside of the Earth's surface as lava solidified. And so some examples there's a basalt. This is pumice, another type of lava rock. And the, the shiny obsidian. All right, so if it's molten rock, but if it's inside the earth, it's termed magma, and if it's outside of the earth, then it's termed lava. So if you see a volcano erupting, do you go, hey, look at all that magma, or hey, look at all that lava? Well, if the molten rock is on the outside of the earth, then you're going to call it lava. That's igneous rocks. How about sedimentary rocks? Well, sedimentary rocks are formed from sediments. As materials are washed by running water, eventually they get deposited, they slow down, they settle down, and those particles build up over time and they compress, and under that pressure, they're cemented together. So a couple examples here, the sedimentary rock limestone and the sedimentary rock shale. So sandstone, shale, siltstone, and limestone are all examples of rocks that were originally transported sediments. This is your textbook view of the Grand Canyon. And if you look straight on at it, you can see that at one time, this area was an ocean and sediments were laid down over millions of years. After a period of uplift, they were exposed and eroded down. But you can still see that those are layers of sediments. All right, how about metamorphic rocks? Well, metamorphic rocks are when rocks change from either an igneous rock to a metamorphic rock or from a sedimentary rock into a metamorphic rock. Metamorphic means the change in the shape. Usually with metamorphism, the original rock is melted and changed to be a harder crystalline rock. And a good example of this is how shale can be metamorphosed into slate, and limestone rock can be metamorphosed into marble. And then you can take the marble and build the Taj Mahal out of it, or kitchen countertops, and so forth. Well, in understanding the changes that rocks go through, there's an entire rock cycle. Really, since it's a cycle, you can jump in anywhere. And usually, what I like to do in the classroom is have students tell me the story of how one type of rock can become another type of rock. For example, can an igneous rock turn into a sedimentary rock? Tell the story. Well, here on the chart, let's take a look. Okay, here's my igneous rock, and it was formed from magma. And so you can turn it into a sedimentary rock by, well, first the igneous rock has to be weathered, weathering and erosion, uh, transported by running water, and then later deposited somewhere else into layers of sediment. And then over time, those layers of sediment become lithified and compacted, and they form sedimentary rock. So an igneous rock can change into a sedimentary rock. Okay, well, can a sedimentary rock turn into a sedimentary rock? Well, if it was a sedimentary rock to begin with, could it still turn into a different type of sedimentary rock? Well, sure. What would the processes be for something like that? Well, say you had sedimentary rock, and once again, through weathering, erosion, transportation, and deposition into layers of sediment, and then over time, that those new layers of sediment would be compacted and lithified back into a different kind of sedimentary rock. Okay, well, can a sedimentary rock turn into a metamorphic rock? Well, sure, like our limestone turning into marble, sedimentary rock, given enough heat and pressure, will recrystallize into a type of metamorphic rock. Well, then can the metamorphic rock turn into a sedimentary rock again? Well, sure. Again, through the rock cycle, the metamorphic rock can be weathered and eroded and transported and then deposited into layers of sediment. And then it can be compacted and lithified. So the metamorphic rock has turned into a sedimentary rock. All right, so this is the rock cycle. The new textbook shows a little bit better graphics there, although I like the flow chart a little better. Okay, but I think that you have all of the different ways that you can have one rock type turning into another rock type. Okay, well, concept check time. And so I will ask the class here, name any sedimentary rock. Okay. Now name any igneous rock. Do you have to look at your notes? And then name any metamorphic rock. Well, remember here in Geography 1010, we're social scientists, and all of this geology has to have some importance for people. So let me ask a couple students, how are rocks and minerals important to people? Certainly building material is one. We eat rocks? Do we ever eat rocks? Sometimes we do. And then how about this one as a multiple choice? Fossil fuels. We'll have to talk about natural resources some other time. But fossil fuels are usually found in sedimentary rock. Oh, I gave away the answer. All right. Okay, so that's the concept check. And I'm thinking that if you graduated high school around here, likely at some point in a science class, you learned the difference between igneous, sedimentary, and metamorphic rocks. And here's a little practice quiz. You could stop the video and see if you could answer these. All right, coal is a sedimentary rock. Slate is a metamorphic rock. Used to be we would have slate blackboards. Uh, Now we have all those marker boards. Granite is an igneous rock. Very often you see tombstones made out of granite because they're hard and resistant to erosion. Shale is a type of sedimentary rock. Marble is a type of metamorphic. Remember when limestone turns into marble? And basalt is an igneous rock. Limestone, of course, is sedimentary. All right, so that's a concept check question. The odds are you would probably pull a question or so about the different rock types. Well, what happened here? If you'll give a listen to the natural environment, the natural history of the Grand Canyon in this case is just screaming out at you that at one time this area was an ocean and sediments were laid down and they were hardened into sedimentary rock. And then there was a period of uplift where those rocks were well above sea level, and then the erosional cycle started wearing them down and incising the canyons. All right, so the Grand Canyon has been around for millions and millions of years. Certainly, a lot has happened there. Okay. Next up, I want to talk about a pretty important topic in understanding landforms, and that's plate tectonics and continental drift. But remember, we're social scientists here. We have to think about continental drift as how is this important for people? The so what of it is why is it important for humanity? Uh, The theory of continental drift was invented by the the famous geographer, geologist Alfred Wegener. And he looked at the globe and he saw that, it looks like South America and Africa kind of fit together like they're a jigsaw puzzle piece. And some of the other continents as well, they kind of look like they fit together. Could it have been that at one time uh, South America and Africa were attached together? Well, and he theorized that, and today we know that that's true. Well, what this series of diagrams shows is the breakup of Pangea. Now, every physical geography book and every earth science book always shows the breakup of Pangea. But you have to wonder, well, what happened before Pangea? Well, bits of continents were spread out along the globe and they all jammed into each other and formed this big supercontinent. This demolition derby of the continents has been going on through all of Earth history. All right, but looking at the recent breakup of Pangea, here you have a sequence about every 65 million years. Uh, Here, Pangea is broken up into two continents, Laurasia and Gondwana land. And then here, 65 million years ago, this is around the time of the extinction of the dinosaurs. And this is today. You can see 65 million years ago, there's this little piece of continent that someday will be India. Australia is still attached to what would be Antarctica. Well, India uh, drifts and crashes into Asia, heaving up the greatest mountain range in the world, the Himalayas. All right, so continental drift operates on time scales of millions of years, really tens of millions of years to get the continents to appreciably change their positions. Well, Wagner's idea of continental drift were actually scoffed at for a long time. It wasn't until the 1950s when the ocean floor was mapped and these divergent plate boundaries were found that it was understood what the mechanism could be to cause entire continents to move. Previously, it was just thought the continents have always been in the same place all the time. Okay, so looking at the this diagram here, you have the continents are floating, if you will, on denser rock. The continents and the ocean basins are floating on denser material of the lithosphere. Now I say float, but not really float in water, not in this case. But there you have lighter rocks on top of denser rocks. As you go down into the mantle, then the rock is molten. So lighter rocks on top of denser rocks. The Earth's crust is broken up into a number of tectonic plates. And these plates move around. And when they move around, they may crash into each other at a convergent boundary. The plates may move away from each other at a divergent boundary. They may slide past each other in some type of transform boundary. And let's see what happens here. Zeroing in on this little cross section of the Nazca plate. Well, it's running into South America, and as it does that, that plate is subducted below the continent, and that's helping to heave up the Andes Mountains. Now, out here at the East Pacific Rise, you have plates that are moving apart from each other, and new seafloor material is being made there. We may have to come back to this map of the plates. Now there's a big divergent area that runs around the globe, kind of like the seams on a baseball, runs down through the Atlantic Ocean. There's a term for that, the Mid-Atlantic Ridge, and we'll take a closer look at that here momentarily. This is a diagram that shows, well, what can move whole continents sitting on ocean basins? Well, it's a process called convection. You will see convection again in the course when we talk about the atmosphere, but heated air rises, and then warm air rises. That's a convectional cell, or a convectional current that can be created. But also convection can occur in liquids, and uh, these rocks are molten, so kind of like a liquid. Well, how it works is this. The core of the Earth is very hot. It still hasn't cooled down since the origin of the solar system. And the rocks above that are heated, or boiled, if you will. And so these plumes of molten rock come up, and in this case, this is along a divergent boundary, or it's um, forcing those plates apart from each other and building more seafloor. In other areas, you have a convergence. So, for example, here, since this plate is moving, it could crash into a continent, be subducted below, and then mountains could be heaved up, and volcanoes could also occur. It might be better to take a look at this in a animated form. And here you can see that the new seafloor is being created. It's the well, it's big convection cells driven from the heat of the Earth's core. Maybe you can make your own GIF. So it's testament to the power of continental drift that if you climb the highest mountain in the world, if you go up to the top of Mount Everest, chip away the ice, and so that you can see the rock, what you're going to find there in places is fossil shells, fossils of marine organisms. Well, how do ocean shells get up to the height of a flying jetliner? How do they get up to what we call the Himalayas as being the roof of the world, or the top of the world? Well, India at one time was a continent, and it was being driven by plate tectonics, crashed into Asia. When it was a continent apart from Asia, there was an ocean in front of it, and as it moved, those rocks that were part of that ocean basin got crumpled up, accordion-like, forming the Himalayas. All right, what about the not where continents are crashing into each other, but where they're being pulled apart? For example, here the divergent boundary, the mid-oceanic ridge runs around the Earth like the seams on a baseball. One important part of the world is Iceland. Iceland is a volcanic island, so where these plates are spreading apart, molten material came out of the surface, and an island is built up there. Iceland today is a has active volcanoes and active hot springs and geysers. All right, so the question here, in case you get that one, well, along a divergent boundary, where would the youngest rocks be? Well, that'd be close to where the opening is. And the oldest rocks are further away. This is a map of earthquakes. Each one of those dots is where there was a major earthquake. And if you look at a world map of this, you start to see a pattern. And it looks like the map of the earthquakes and volcanoes too kind of trace along where the plate boundaries are. You know, a good place to see that is the Pacific Ring of Fire, so termed because of all of the tectonic activity that characterizes the circum-Pacific basin. There's a lot of earthquakes and volcanoes, and so Japan is a volcanic archipelago, volcanic islands. The Philippines, what are they? Volcanic islands. And so the mountains of the Andes are built up by plate collision. So you have a lot of uh, tectonic movement, earthquakes, and then also a lot of the tsunami. They're formed by the underwater earthquakes. And so, because of those natural disasters, the circum-Pacific region is sometimes termed the Pacific Ring of Fire. All right, here's a detail of a subduction zone. With any luck, you'll pull the question on both the quiz and the midterm about what subduction zones are. The plates have collided. One plate is denser and it's subducting below, and then gravity takes over, starts to pull it down. But as it does that, it gets heated and it melts, and molten material comes back up in the mountain forming process of volcanism. That's a subduction zone. Well, you won't see this question on the final. Took it out of the test bank, but it's from my retired test bank files. Why is it important to humanity? Why is the concept of plate tectonics, continental drift important to humanity? Well, the best answer is C. Or earthquakes, volcanoes, and tsunami, other tectonic movements are caused by plate movement, and these directly affect human lives. So we live on an active Earth. Even though the continents are moving on average at about a rate that your fingernails grow, well, there can be sudden movements and sudden upheavals that affect human livelihoods. And we should plan for that. We should plan for these earth movements. Let's take a short break and then we'll move on to part two.